Imagine a world where computers can solve complex problems in a fraction of the time it takes today, revolutionizing fields like medicine, finance, and climate modeling. This is the promise of quantum computing, and the Cornell Quantum Computing Association, QCA, is at the forefront of making this vision a reality. Just 2 years ago, QCA didn't exist, but today it's a thriving community of over 30 active members, divided into 3 teams: algorithms, theory, and hardware. Each team shares the same goal: to educate students and build projects in the field of quantum technology. But here's where it gets exciting. QCA is one of the few undergraduate groups in the nation building and publishing their own findings in quantum hardware. Quantum computing is an emerging field that uses the principles of quantum mechanics to process information using qubits, which can exist in multiple states simultaneously. This property enables certain problems to be solved much faster than with classical computers. As Haadi Khan 27, president of QCA, puts it, "We're trying to build something that doesn't exist anywhere else." Quantum computing is a mix of computer science, physics, and math. And we're creating a space for students to actually explore that, hands-on. Haadi joined the club in the spring of 2024, drawn by his interest in computer science and physics. Austin Wu, 27, co-founder and vice president hardware lead of QCA, started the group early in his freshman year. QCA is divided into 2 separate components: an education side and a research project-focused side. The educational side plays a vital role in the club, offering lectures and problem sets similar to those found in an introductory quantum mechanics course. Since most students join with limited prior knowledge, this lecture series ensures that QCA members are equipped with the base knowledge required to contribute to advanced research projects. The education side offers a series of lectures and practice problems, introducing students to quantum mechanics, the branch of physics that specializes in how energy and matter behave at the atomic and subatomic scale. In the spring, the club has a deeper emphasis on the technical aspect and hosts a series of workshops. Compared to the fall, which has an emphasis on fundamental theory, spring workshops place a greater emphasis on the technical aspect of implementation, coding up quantum algorithms, designing hardware such as circuits, and understanding academic research papers. All new members have to participate in these courses, which are taught by Haadi. But this is the part most people miss. QCA's research project focus side is working on cutting-edge research, particularly in the design of a novel quantum memory device, a system that has the potential to significantly improve how long quantum information is stored at room temperature. Currently, this is QCA's biggest project, and it involves building an entirely student-led experimental setup using custom fabricated optics and circuits. Most systems store quantum information for around 100 milliseconds, Wu said. "We're aiming for an hour. We're hoping to break a few records." The team believes that this is feasible by enhancing and experimenting with optics and circuit design to store quantum information more stably than previous systems. And this is where it gets controversial. Some experts argue that the pursuit of quantum computing is a waste of resources, given the significant technical challenges that must be overcome. But QCA's team is undeterred, driven by their passion for innovation and discovery. Beyond the hardware team, the club's theory team is working on topological quantum error correction, a way to preserve information in fragile quantum systems by layering in protections onto fault-tolerant codes. "You'd normally only study this in a graduate math class," Wu said, "but we're doing it as undergrads." On the other end, the algorithms team is focused on quantum approximation algorithms, specifically working on problems related to QAA, a framework designed for near-term quantum computers. They're doing stuff in QAA, which is like quantum approximation algorithms for near-term computers, Khan said. Since these algorithms are fitting for the current limitations of quantum hardware, this enables the team to engage in ongoing research practically. QCA works on these projects in the basement of the Physical Sciences Building, in collaboration with Prof. Katz's lab. QCA aims to be able to eventually publish its products in a high-impact journal. Members of QCA handle everything from behind-the-circuit design and fabrication to understanding past literature and simulation. We read academic papers every week and talk about how to implement the ideas ourselves, Austin said. But here's the challenge. This ambitious work is not without its challenges. As Haadi noted, it's a major time commitment. I probably spend 10 to 12 hours a week on QCA, and the funding is tight. Physics hardware is really expensive. In light of these challenges, Haadi highlights the unique drive within the club. When someone hits a wall, the instinct here is to work harder, Haadi said. That's what makes this club different. In the future, QCA aims to be able to publish their research, increase funding, and inspire undergraduates to exceed their limits. If you're curious and want to teach yourself something challenging, Haadi said, this place is for you. So we have to ask, what do you think is the most significant challenge facing quantum computing today? Is it the technical hurdles, the funding, or something else entirely? Share your thoughts in the comments below. And if you're interested in learning more about QCA and their groundbreaking work, be sure to check out their website and follow their journey as they push the limits of what's possible in quantum computing.